Redis is an open source in-memory key-value database. It also happens to be blazingly fast. In my current role, we have a Redis cluster that caches HTTP responses from a third-party dependency. This cluster, at peak times, handles around 2 million requests a minute, which is pretty impressive. This typically has been one of the more common use cases of Redis that I've come across, speeding up I/O-based operations by adding a caching layer in the application stack. But Redis can be used for so much more than this single use case. In fact, I'd go on to say that using Redis only in this capacity is a waste of its talents. So in this video, I decided I wanted to look at some misconceptions about Redis, and how we can replicate database functionality with it. The first question I want to answer is, how did we get here? Why has Redis so easily been relegated to the caching layer instead of being the actual database itself? And why does my coworker flinch whenever I mention using Redis as the primary database? Well, I think there's two common concerns when it comes to using Redis as a primary data store. The first is because Redis is an in-memory database, which implies that the data must be ephemeral. The second is that because it's a key value store, well, it cannot handle complex data structures or queries. Let's take a look at each of these concerns. The reason Redis is incredibly fast is because it stores its data in memory, rather than on disk. Now, if you know how computers work, you're probably aware of why this may be a bad idea to use Redis as a primary data store. If the instance is destroyed, the memory is wiped and the data lost. Or is it? Let's actually test this out. Here I have a single Redis node set up on my home lab Kubernetes cluster. Yes, I finally have a dedicated home lab now. Let me know if you're interested in my setup and I'll happily do a video on it, maybe on another channel. Let's go ahead and connect to it. I'm using Kubernetes for this cluster, so it's easy enough to port forward and connect in. Okay, so we're inside of our Redis instance. If I run the keys command, you can see that it's completely empty. Let's add a new value using the set command. Here we're going to set the key of power level and the value to be just over 9000. If we run the keys command again, we can see the power level key now exists, and we can retrieve the value using the get command. Now it's time to apply some chaos engineering. Let's go ahead and delete our Redis instance. After a short while, a new Redis instance comes back to life, due to the power of Kubernetes. If I go ahead and connect to this new Redis instance, and run a get command against the power level key, we should receive a nil back. However, that's not the case. So what gives? How does this data still exist even after restarting the Redis instance? Well, it's because Redis actually has persistence built in. In fact, there's actually two different types of persistence that Redis uses. The first method is snapshotting, which is known as RDB. This is a point-in-time snapshot of the dataset at specific intervals, similar to the snapshot feature found in other databases. Whilst this method is good if you need to restore your data to a point in time, it's not what is actually bringing our Redis instance back to the same state as before we crashed it. That behavior is handled by the second persistence method, called AOF, which stands for Append Only File. When configured to use an AOF, Redis will write an entry to a log file for every write operation the Redis server receives. During a restart, these operations can then be replayed, reconstructing the original database. This is actually similar to how Postgres stores data using WALs, or write-ahead logs. In fact, the Redis documentation claims that both the AOF and RDB persistence will give you a degree of data safety comparable to what Postgres can provide. Now, that's a bold claim, but I'm inclined to believe it, certainly based on the real-world experience of using Redis at scale. Okay, so data persistence in Redis can be set up to be as comparable to one of the safest databases out there. But what about the second reason to not use it as a primary database? The lack of complex data structures. In a typical relational database, we're used to abstractions such as tables, rows, and columns. In addition to these, we have indexes, partitions, primary keys, foreign keys, and many others. All of these concepts allow us to query for data and perform complex operations. When it comes to Redis, it's much more simple, but that doesn't mean it's any less powerful. Redis is much closer to the abstractions found in traditional computer science, such as arrays, hash maps, sets, and many others. These data structures are used by traditional databases to create the actual abstractions we know and use, and therefore we should be able to recreate them using Redis. So to do that, let's go ahead and actually look at some of them. The first thing we're going to do is replicate a simple user table, which contains a user ID and an email address. In SQL, the table would look something like this. We can easily recreate this in Redis using the basic operations of set, which allows us to store a record as a key value pair. So we could just set the user ID as the key, followed by the email as the value. That would get us what we're looking for, but there is a problem with this implementation. As Redis does not have any logical groupings or even schemas, then we lose the information about what we're storing when we store the ID as a key. For example, this UUID could be related to a user, but it could also be related to a product or an order. There's no way to tell without actually looking at the data itself. And even then, there's still a chance of losing the information about what you're storing. Therefore, it's a good idea to specify the data type in the actual key, sort of like a namespace. The idiomatic way in Redis is to use a colon to separate the namespace from the identifier. So in our case, it would be user:ID. This way we provide some additional context about what the data type is that we're storing. But it also has some other benefits. Let me explain with a typical scenario you'd find within a web app. User authentication. In this case, we want to perform authentication with a user's email and password. Currently, we can obtain a user's email address with their ID, but that's no good in this case. We actually want the inverse, which is obtaining a user's ID given their email address, if it exists in the database. So how can we do that in our current database setup? Well, the naive approach is to search through all of the user entries by using the keys command for everything in the user namespace. We could then iterate through every entry and check if the value matches our email. If one does, then we have the user ID. By the way, in a production system, don't use the keys command. It can and will lock up Redis, which will block any other queries from completing. Instead, you'd use the scan command, which is a little bit more complex, but it allows you to iterate through cursors. For testing within this video though, the keys command is absolutely fine. This method of comparing each record's value in the user namespace against our input is called a sequential scan. This works similar to how a SQL database would perform the same operation. It's not the most optimal method, however, as it can take a long time to scan tables that have a large number of rows. To improve performance, you would use a database index on the email column, which acts as a sort of lookup table, storing the user's email with a reference to the associated row ID. If this sounds very similar to a key value pair, well, that's because it is. And that means we can easily replicate it using Redis. One approach to implement this would be to store a key of the user's email with an associated namespace, and a value of the user's ID. With this, we can easily obtain the user's ID from an email input using the Redis get command. But that's not the only benefit this model gives us. We also have a sort of unique constraint, in that we're able to also see if an email already exists in our system. There is a better data structure to use for unique constraints, but more on that later. So we have our simple table and a pretty fast index. But if this was a normal application, we'd want to store more data than just the user's email address. We'd likely want to store the user's name, a hashed password, and other fields. So keeping with the authentication model that we've played around with, how do we store the hashed password in our table? Well, we could do this using another key value pair, where we store the hashed password against the user's ID with some namespaced prefix. But that's not really scalable. Another option would be to store a JSON encoded string of our user's data structure as the value to the user's ID. This works, but it does mean every time we want to add a new field to our user, we would have to fetch the record, decode the existing value, make the change, re-encode it, and store it using the set command. A better option is to use the hash type for our value. A Redis hash is basically a dictionary, or a hash map in other languages. It allows us to store a more complex data structure against a key. Here we're going to use the hmset command to store multiple hash key values against a single key of our user ID. Fields we're going to set are email and hashed password. The values for each of these are defined after the field's name in the command. We can then retrieve this full structure using the hgetAll command, which takes in the primary key. Here you can see we have our full data representation of our user, which we just previously set. If we use the Redis SDKs in different programming languages, we can easily decode this into native data structures as well. Here's an example using Python. What's really awesome about this approach is if we want to add additional data to an entry, we can easily do so using the hset or hmset commands. For example, let's add a name to our user's entry. Just as we can add fields, we can also delete them using the hdel command. Although one thing to note is that the hash will no longer exist if no fields remain. Using this data structure, let's look and see how we would handle a simple authentication flow. First, we find a user ID given the email address provided. If one doesn't exist, then we return false. Next, we can use the hget command to get the user's hashed password from their user ID hash. And finally, we could verify this hash password against the password submitted. And we've ended up with something that looks very similar to how you would interface with a typical database. So what next? Well, we've looked at tables, sequential scanning, and some basic indexes. But what about ordering? In a typical database, you may want to return values based on a timestamp or a ranking. To showcase this, let's first set up a counter for our users to track the number of times they've logged in, or something. We could add this to our user map, but it's going to be more powerful to add it to another data structure. This data structure is the sorted set, which allows us to store unique members, which would be our user IDs, with an associated score, which, in our case, would be the number of logins per user. To get started with the sorted set, we can use the zadd command, which will insert a member into the data structure, creating the sorted set if it does not exist already. The first argument for this command is the key we want to use for the set itself. In our case, this will be the user logins. We then set the score, or login counts, we want to associate with our member, which in our case is going to be 10, and finally the member itself, which will be our user's ID. We get back the value of 1, which tells us we successfully added a single member. We can retrieve this entry by using the zscore command, and passing in both the key for the set, followed by the key of the member. Here we get back the value of 10. As well as using zadd, we can also use the zincreby command to both add members to our set, or increment the score of existing members. If a member doesn't exist, then it is added to the set and given the increment value as its starting score. In our case, we've added a new member to the set with the initial value of 7. That covers how to add entries to our set. Next, we're going to look at how to perform some range operations over the data within. Before doing that, I'm first going to add 3 other members to our set, each with different scores. Now that our member's added, let's ask some questions. The first is we want to order our users by the number of times they've logged in descending order. We can achieve this by using the zrange and the zrevrange commands. This allows us to select members by range of their sorted indexes. If we use the zrevrange command with the values of 0 and -1, we receive a sorted list of our members in descending order. So how does the zrevrange command work? The first parameter is the starting index, which in our case is 0, and the second parameter is the ending index, which in our case is -1, which means to go until the last member. If we wanted to retrieve our members sorted in ascending order, well, we could use the zrange command instead. We can also scope this command to retrieve only a subset of our members. Let's say we want to retrieve only the top 3 most logged in users. We can do so by using the zrevrange command with the values of 0 and 2. We can do the same to retrieve the 3 least logged in users by using the zrange command with 0 and 3. As we're directly selecting indexes, you may want to know how many members exist within our set. We can retrieve this number by using the zcard command. Using these 2 range commands, we can easily sort our members in either ascending or descending order, whilst also limiting the number of results we get back. Very similar to the SQL you see on screen. This only applies to the sorted indexes, however, basically the relation of each member to one another. There may be situations where you want to filter based on the actual score value itself, similar to using a where command in SQL. For example, we may only want to retrieve users that have logged in greater than 10 times. Well, we can actually do that by using the zrangeByScore command, followed by the min, which in our case is 10, and the max. To ensure no upper bound, we would just use the +infinite value. This will return the 2 members we have that are greater than 10, sorted in ascending order. If we want to retrieve the members in descending order, we can use the zrevrangeByScore command instead. We also need to swap the position of the parameters as well. We can also use these commands to retrieve our least logged in users. To do so, we'd instead use the -infinite value when specifying the min range we're looking for, and setting our max value appropriately. In our case, we're setting the max to 5 in order to retrieve any members that have logged in less than or equal to 5 times. So great, we not only have sorting by values, but we also have filtering by range as well. We achieve this by using sorted sets, but there's another type of set in Redis we can use for unique constraints. This is the standard set, which stores unique members inside of it. Earlier, we created a unique index for our user emails using just a key value pair. But what if we don't want an index, but instead only want a unique constraint? For example, let's say we want to allow our users to select a username, but we want to have unique instances of usernames within our database. By using the sadd command, we can add username values into our set, creating the set if it does not exist already. Then, let's say when a user goes to set their username, we can use the sisMember command to check if the username is available. If it already exists within our set, we get back the response of 1, which represents true. Otherwise, we get back the result of 0. The set works as a sort of replacement for a unique constraint, but it does require storing related data across 2 different structures, which adds complexity to our data model. So the last database concept I think worth touching on is actually really important when it comes to Redis, perhaps even more so than normal databases. That concept is transactions. In databases, transactions are used to group operations together in an atomic fashion, i.e. either all of the operations perform or not at all. This concept is very important as it prevents us from being left in a partial state. To visualize this, let's look at some example code for creating a new user. We first check to see if the user's email already exists. If it doesn't, then we proceed with adding the user entry followed by setting the user's email to ID mapping. This code is susceptible to a race condition, however. In rare cases, it's possible that in between the time we check if an email exists and then set the user's ID for that email, another entry could have been written. This means that our second entry will overwrite that existing one even when it returned a success to the user. This is very bad. However, we can prevent this by setting the NX option, which stands for not exists, in our Redis set command. What this does is enforces the set command to only apply if the record does not exist already. This prevents us from overwriting the original record and lets us know if we encounter an error. However, it does leave us in a partial state, where our user record was created when it shouldn't have been. Now, we could resolve this using reconciliation, which is where we unwind our partial state and remove any created entries. But this adds a lot of complexity and can still be prone to errors. It's much easier to use a database transaction, which fortunately Redis does support. Let's look at how to use them. To begin a transaction, we first need to call the watch command on the key we're interested in. In our case, this is the user email key that we're going to set up. The watch command will cause any transactions to be discarded if a change is made to the watched key from any other client. Once we have our watched key set up, we can enter the transaction using the multi command, and we can confirm that our client is in a transaction with the letters TX next to the prompt. Next, we can go about adding our user hash using the hset command. Now, to simulate a race condition, I'll open up another client to Redis and set our user's email to point to a different user ID. This is the key that we're watching. Back in the original client, we'll also attempt to set the user email index key, but point it to a different user ID. Finally, we'll run the exec command to apply the transaction, which returns nil, letting us know that the transaction didn't apply. We can validate that our user email points to the existing user ID, and that our user model was never created, showing us that the transaction worked as intended. Now that we've taken a look at how Redis can be used as a primary database, it's probably worth talking about a couple of reasons why it may not be worthwhile to do so. The first of these is that when it comes to Redis, there's a significant amount of work that needs to go into creating what databases give us for free out of the box. Take Postgres and SQL, for example. Setting up tables, indexes, and constraints are all achieved declaratively using a powerful query language. This contrasts to Redis, where each of these operations has to be built using the primitives that Redis offers. That being said, it is a good thing to learn how to implement these features using primitives. But if you know you're going to need these complex data structures and want to get started quickly, then a database like Postgres is going to be a better choice. The second reason that I would opt to not use Redis is actually due to the fact Redis stores all of its data in memory. Earlier, we covered that Redis storing its data in memory is much safer than one may initially think. However, there is another elephant in the room. Memory tends to be much more expensive and less available than storage, considerably so. This means you'll likely end up paying more money for using Redis when it comes to larger datasets, either by horizontally or vertically scaling your Redis instances. However, if your dataset is small or you need to be really fast, then Redis may be worth that additional cost to you. For me, well, on personal projects, I typically couple Redis with Postgres often, usually as the caching layer before the database itself. My datasets also happen to be rather small. Therefore, in the future, I will likely consider promoting Redis to the primary database on my initial iterations, and only migrating to Postgres when I need to. Either way, I'd love to know your thoughts. Has this video convinced you to try Redis as a primary database, or were you doing so already? Let me know in the comments down below. Otherwise, a big thank you to my channel members, including my newest one, Canarius, and a big thank you to everyone else for watching. I'll see you on the next one.